이걸 다음에 프로젝트 한번 올 때 단가를 좀 한번 해놔야 되는데 내일 오후에 그 얘기를 한번 해드릴게요. 프로젝트 우리가 가끔 올 때 단가를 하잖아요. 그런 것도 자꾸 프로젝트 그렇게 있는데 할 때마다 도와줘야 되거든요.
하루에 얼마씩 일하고 이것처럼 바로 레이스잖아요.
그러니까
이거 얼마나
그래서 나도 내일 들어오면
800불. 800
하루에
800유로.
하루에
네, 5,840, 800유로.
그러면 뭐 사람마다 그렇게 계산하면 좀 힘들고 사연서 써주시면
120만.
사연서 써주는데 얼마, 뭐 계산해주는데 얼마 그런 거를 저희를 우리가 먼저 하고
네.
LF 뭐 EAF 해가지고 그렇게 하는데
사람은 우리 생에서 다 끝나지 않겠어요?
사연서는 그렇게 좀 다른 것들 좀 지휘할 거는 있을 수 있잖아. 오케이 스타트.
Okay.
이거 쳐야 되는 거 아니야? 이렇게 take it.
So we come to the material balance. And you have to know that there is no good thermal balance without a good material balance. Yeah, because the energy depends on the material you are charging in a furnace. So that's why it's important to know what kind of scrap the customer is going to charge. So in the first part here, you have the material input here. Here the material output. And here the balance of each element. So you see here on this table that all is equilibrated, almost. Yeah? And on this side you have some, let's say, main figures. That means, for example, you will have a total of 32 kilograms of carbon involved in the reaction. That means we bring 300 kilowatt hours per ton of energy, and we require 60 cubic meter of oxygen to burn into CO2. Yeah? And here you see the iron. In fact, this is the iron oxide. Yeah? And it is the balance between the iron oxide, which is brought by the material input, in this case the DRI, and what will remain in the slag as iron oxide. You have a negative figure just to show you that you will reduce 1 kilograms of iron. Okay? If, for example, here I put something like 80% of DRI, of course I have to remove some other scrap, otherwise you see it's getting red here. You see, it is jumping quite a lot. Yeah? And of course, you have to provide more energy. Okay? And the carbon will be, let's say, adapted accordingly as well. We will see the carbon calculation later. And we have turnings.
저 어디다가 에너지를 더 넣어줘야지.
밖에서 에너지를 줘야 되는데.
Michelle,
I'm not understand the reduced. Why the FA is reduced?
그렇죠. FE를 오를 빼.
Because when you are
Actually, FA he didn't change. He will stay as it was.
when you are using 80% DRI,
Yes.
in the 80% DRI, you have seen that
DRI 자체가 FEO잖아.
you have 90% or even 92%
You mean from total FA?
utilization rate. Oh, you have 90%, let's say. So you have 12% FEO.
Yes. From that you mean?
Mm.
Ah.
in the raw material.
there is not
If you take this 12% FEO
yes.
and you take this and you put this directly into the slide, you will have 50% FEO in your slide or 60% FEO in your slide. And you increase the slide amount, so you will lose a lot of material.
From slag.
저게 FEO가 지금 얘기하는 건 FEO 있는데 저게 슬랙으로 다 가버리면 안 되잖아요. FEO가.
If you don't do anything, let's say you charge the DRI in the furnace and just melt,
Yes.
the FEO will remain FEO.
Yes.
Some will react with the carbon which is in the DRI itself.
Yes.
But most of the time this carbon will protect the rest of the iron. Yeah. So you will end up with a lot of iron oxide
Yes.
in the slide.
Yes. FPO.
If you want to here, we have reduced the DRI. Yeah. Let's study again this. No, it was 60%. 70% even. All right. If you, I don't do anything. I try to have it here at 0. Okay. Okay, it's almost balanced, yeah? All right. So you see, I will end up with 43 plus 12 is 55% FEO in the slide. That means in this charge I will lose 13 tons of iron in the slide.
Yes.
실수리 감소하는 거지. FEO로.
So I want to not to avoid this because I paid the iron from the DRI.
Yes.
So in order to avoid this, I will inject carbon.
Yes.
Or charge carbon to reduce this FEO.
From slag, you mean?
From the slag.
That means
그러니까
지금 minus FE means from the amount of FE from slag, you mean?
Yes.
Yeah. Then I understand.
It's not slag at least. It's coming from the iron balance wherever it comes.
Yeah. You mean in case of the DRI, the FEE is FEO remaining in the molten steel, yeah. And if we do not any actions, the FEOs can be changed to the slag, and we can lose so much FE.
Yeah.
So we inject carbon and we have to remain the FE inside the molten steel and CO come to the slag.
Yeah. CO come to the gas.
DRI는 다른 케이스라 FEO를 아무 액션 안 하면 FEO로 그냥 남아 있는 거지.
그렇죠. FEO가 슬래그가 있는데 그게 O가 떨어져 나가고 이제 시험.
아니 슬래그 속이 아니야. 슬래그 속이 아니고.
네,
아니고 DRI 자체에
올라옵니다.
DRI 자체에 FEO는 FEO로 그냥 남게 되는 거라.
예.
남게 되는데 우리가 아무것도 안 하면 이 FEO가
슬래그
슬래그 쪽으로 올라가 버리는
그래서
거야.
안 했어요.
반응이. 그러면 이 우리가 FE의 실수율이 떨어지잖아.
예.
그지? 그러니까 거기다 이제 카본을 넣어서 CO 반응을 이렇게 해서 이거는 가스로 나오든지 슬라그로 가게 하고 FEO를 뜻을 남게 해준다는. 그래서 이제 에너지가 더 필요하다 이제 그런 얘기니까 이런 거지.
그 이제 흡열 방송.
다른 거는 스크랩이란 개념이.
그러니까 그 흡열 반응이라는 게 FeO에서 O를 빼내기 위해서 열이 들어가면 그만큼 더 들어간다는 얘기야.
그렇지, 열이 더 들어간다. 그런 의미지. 그러니까 이제 DRI의 반응이 틀리다는 거야. FeO 자체는 그대로 남아있다가 슬라그로 갈 수 있으니 카본을 계속해서 넣어줘야 된다는 거지.
And,
Yeah,
you,
okay, keep going.
and you see that the amount of slag is tremendously high, yeah? 200 kg per ton.
Yeah.
Where if
It's like a stream, yeah? In DRI, EAF.
so that's why you see that I want to reduce this iron oxide. Yeah?
Of course.
Yeah.
Of course.
Could you explain one more time about HMS1? The HMS1.
Where?
스크랩 그레이드.
Heavy melting scrap.
Heavy melting scrap.
네, 웨이팅 스크랩
Yeah.
근데 다른 거는 그냥 좋으신 것 같은데 저거는
아, 저거는 크게 정해진 게 있어. 그 나중에 거기 봐봐. 우리 기준 지난번에 비나할 때 받았잖아. H1, H2 뭐 이렇게 다 받은 거 있다. 그 자료를 보라고.
브리티시 스탠더드, 어메리칸 스탠더드, 뭐 세계 나쁜 HMS 뭐 이런
그냥 쉽게 얘기하면 우리 앞에 빌레트나 슬랩 앞에 자른 거 있잖아. 커팅에 자른다고 뭐 좀 해두고 뭐 그런 것들 정도 다 생각하는데
저게 캘큘레이트 되는 거라고 그 있잖아요.
아니야. 저거 자기가 실험을 여러 번 해가지고 HMS1만 여러 번 녹이가지고 다른 거 안 넣고 그래서 만든 데이터야. 오케이. Keep going. I explained his question.
So let's concentrate now on the material balance itself. The carbon, this is the steel analysis. Yeah? The carbon content of the steel is given by the input. Yeah? This is my target carbon here. Okay? Silicon is assumed to be 0 because we are oxidizing. We are not in case of stainless steel. Yeah? Mangan is calculated by the mangan balance. You see here, you have the coefficient, partition coefficient of phosphorus, sulfur and mangan. Okay? So in fact, you see the mangan here, the MnO. Is given by the amount of slag times the content, and this is given by this value times this value. Yeah? I mean the mangan content of the steel times the partition coefficient. And this coefficient is just to convert Mn into MnO. Okay?
Would you please explain the Mn divided Mn equal 55?
This is the partition coefficient, which
슬랩이
means
약하고
this is the mangan in the slag divided by the mangan in the steel. The phosphorus in the slag divided by the phosphorus in the steel. The sulfur in the slag divided by the sulfur in the steel. Yeah?
슬라그랑 스틸에 있는
And this one,
비율
this one is given by this formula. It's proportional to the iron content in the slag, or the iron activity.
그때 54, 355 정도 있어요.
Yeah? All these values are, let's say, related to the basicity, I mean for phosphorus and sulfur, basicity and iron activity in the slag. This is a constant value. In oxidizing condition. the sulfur partition coefficient doesn't vary so much. Yeah, and you don't do a lot of desulfurization in the furnace.
You mean activity is chemical activity?
Yeah.
Okay.
So mangan is the same, yeah, but just related to the iron activity.
And I think it's next time you write down some document when you make a document and the constant in your Excel file. You had better write down what is the meaning, or it is from the experience, it is from the anywhere, yeah, or calculation from where. It's
This partition coefficient, this is thermodynamic. Yeah?
So, but if we find that, for example, 2.31, then we have to we have to find some any thermodynamic books, yeah. But we confused it. So if you write down some memo, 2.31 is from where, and we can confirm it.
No, I mean this is a simplified model.
Simplified model. 그 필요 없겠나? 예를 들어서 뭐 참수들이 있는 거 우리가 기본적으로 좀 어디서 왔는지를 받고 하는 게 나을 것 같은데.
좋죠.
그렇지? 아니 그걸 알아야 우리 작가가 이걸 나중에
예.
소프트웨어를 만들더라도 웹글로 다시 그렇게 할 수 있는 거지. 그지? 이게 나중에는 아까 얘기한 것처럼 영업하는 사람들이 쓸 수 있는 소프트웨어를 간단한 걸 만들어줘야 된다고. 그 다음에 이 프리사이즈 된 거 우리 쪽에 또 맞게끔 또 바꿔야 되는 것도 있다고. 그래서 okay, let's read it. When we received your Excel file and then we studied your all equations and then if we try to know some meaning of the constant and we make a document questionnaire and we send you.
Okay.
우리 그렇게 지리서 작성해서 보내는 걸 그렇게 하자.
So here you see this is a very big number.
Yeah.
And of course I don't put it by hand. This is the result of, let's say, loops. Yeah. You will see in a macro. So the material balance. So this is the slide adjustment. This is what's happening when you click on this button here. Yeah, this one. You start this macro. So we balance the MGO, then the CAO, and then we adjust the slide equilibrium bit for mangan, phosphor, and sulfur. That means this is the mangan, N30. N30 is the steel analysis. This is N30. N30 is this one here. This is the difference. Yeah, between these two elements. Yeah. In percent. Okay, and my goal seek is to put this value to 0. Yeah? By changing, you know the function goal seek. Yeah? My goal is 0 for this N30, and I change the cell C28, which is the mangan in the steel. Yeah? This is clear to you, yeah? This C28. Okay, when I click this button, I change these values here in order to reach 0 here. Yeah? Same for the phosphorus. Difference here to be 0, and I change this value here, you see, it's also a very big number. And sulfur, the same. Okay? So carbon is given by the input, silicon is set to 0, whatever happens, and these values are adjusted by this, let's say, difference. The iron is 100% minus the rest here. And here oxygen, I put some, let's say, the equilibrium of oxygen depending on the carbon and the temperature. This is a well-known formula to calculate the oxygen. So this is the tons I have, and I calculate here the kilograms. Then dust, here it's a constant. The dust amount for conventional EAF varies between, let's say, 15 to 20, 22. 15 to 22. Yeah. 15 is for, let's say, short arc practice, let's say a small transformer, or DRI feeding. No, DRI feeding not so much because you have a lot of fines in the healthcare. For short arc only. And if you elongate the arc, you create more dust. Typically nowadays the furnaces are all using, let's say, UHP, yeah. So they are in a range of 18 to 22.
In case of UHP, the 18 to 22.
Yeah.
노화하고 그 UHP가 이렇게.
Which doesn't make a big difference for the mass balance anyway. Yeah. Because 2 kilograms per ton is 0.2%, so it's not 2 kilograms per ton is 0.2%.
0.2%. 0.2%.
Yeah. So this is a typical analysis from this dust. You see, this is constant. Yeah? Of course, you don't have silicon. You may have a little bit of MnO, so I put it here as Mn. And here the oxygen is related to the Fe and Mn. And then comes the slag. So you have all the oxides here, and we start from the silica. So the silica is given by the total amount of silica brought by the raw material plus the silicon which is going to be oxidized. That means that's the meaning of the 2.139. This is to convert the silicon into silica. Okay. Minus is going into the dust. Alright? So, then we calculate the kilograms. When we know the kilograms of alumina, it's the same. This is the total amount of alumina brought by the raw material minus the alumina going into the dust. Alright? Then CaO. The CaO, this is the kilograms of silica times the basicity.
Okay, just a minute. Okay, I will introduce our boss. 5분?
예.
10분? 10분이면 Let's go. And with the name card?
Yeah.
잠깐 10분 정도 쉬죠.
메테리얼 밸런스가 제일 핵심이거든요. 메테리얼 밸런스가 제일
열심히 마시죠.
그죠?
아씨, 나보고 하나 하나 똑같이 공부해줘.